Greetings, ladies and gentlemen. This is 3.4, limits at infinity and horizontal asymptote. Okay, so let's start by identifying what a limit towards infinity looks like. So first, let's have limit of f of x as x approaches positive infinity. And let's say the limit exists. It's equal to L, where L is some finite number, right? Some finite number. Then what we can say from this is that y equal to L, the horizontal line, is a horizontal asymptote of f of x. Okay, and I'll show you guys a picture in a second. And we also can take the limit to negative infinity, right? Limit of f of x as x approaches negative infinity. Let's say it's equal to some finite number m, right? So m is here also some finite number. Then we can say the same thing about this value of m, right? Y equal to m is a horizontal asymptote of f of x. Okay, so let's take a look at a picture of y equals arctangent of x. Okay, so here is the graph of arctangent, and you can see that as x approaches positive infinity right here, the y value is approaching pi over 2. So what we can write here is as the limit of arctangent of x as x approaches positive infinity is equal to pi over 2. That means y equals to this constant pi over 2 is a horizontal asymptote, right? And as we can see here on the graph, this is the dashed line that is the horizontal asymptote. All right, and we can see something similar for x approaches negative infinity, right? So when we take the limit of arctangent x as x approaches negative infinity, which is on the bottom left here, you can see that the line arctangent x is approaching the value of negative pi over 2 as x approaches negative infinity, right? So the limit of arctangent as x approaches negative infinity is equal to negative pi over 2. And by doing this, or by seeing this, we can also say that y equals negative pi over 2 is also a horizontal asymptote for the function arctangent of x. Next, let's look at another example. We have a graph of the function g of x, and we want to evaluate the limit. On the right, we have 5 parts, A through E. We have 5 limits. We want to evaluate them using the graph. Now, feel free to pause the video and try these out on your own, and take a few minutes to try them out before you proceed. Okay, let's take a look at part A. Part A, it's taking the limit as x approaches positive infinity, right? So when we take the right-hand side of the graph towards the positive side, we do see some sort of a conversion here for part A, where the y value is getting very close to 2, right? So we can say that the limit as x approaches infinity goes to 2. All right, for part B, we're looking at x goes to negative infinity. So if you go to the left-hand side, you see towards this part, going towards the left, it's actually approaching the value of negative 2, right? So as x approaches negative infinity, g of x approaches negative 2. Now let's look at part C. As limit approaches 3, 3 is right here. And you can see that from both sides of 3, the line is actually going up to infinity. Right now, since the left-hand limit and the right-hand limit matches, we can say that limit as x approaches 3 actually goes to positive infinity. Okay? And let's look at 0. This is part C. Right? And let's look at 0, part D. At x approaches 0, again, from both sides, they from the left and the right, they all both go to negative infinity. So we can say that the limit exists going to negative infinity as x approaches 0. And part E, we're looking at as x approaches negative 2 from the right-hand side, right? So negative 2 is right here. Now from the right-hand side, so we want to move to the right a little bit of negative 2 and look at where the graph is. And the graph is down here. Now you can see that it's actually going down to negative infinity, right? So we can say that the limit as x approaches negative 2 from the right-hand side, right? Remember this little plus sign means from the right. Right? The limit goes to negative infinity. Okay. Now, we also have one more part of the question, which is part F, is we want to find the equation of all the asymptotes, right? Find equations of the asymptotes. Okay, so let's take a look from part A. We know that as x approaches infinity, the value goes to 2, right? So if you see here, we get like a horizontal asymptote here, horizontal line, right? So in this case, we get an horizontal asymptote of y equals 2. And from part B, we get the same thing, right? On the left-hand side, we get some sort of horizontal asymptote at negative 2, right? So y equals negative 2. So these two are horizontal asymptote. And from part C, if you recall the definition from chapter 2, when we talk about vertical asymptote, is when any of the limit goes to positive infinity or negative infinity, that's when we have a vertical asymptote at that x value. So for part C, since we get infinity when x is approaching 3, that's where the vertical asymptote is going to happen, right? So the vertical asymptote is going to be the line x equal to 3. And same thing for part D. It's going to negative infinity as x approaches 0. So we get x equal to 0, right? The y-axis as the vertical asymptote. Part E, we have limit as x approaches negative 2 from the right. Now remember, we just need at least one limit that gives us negative infinity or positive infinity to identify a vertical asymptote. So in this case, we can say that yes, x equal to negative 2 is also a vertical asymptote. Okay, so summarizing this, we get horizontal asymptotes from part A and B. Right, and from part C to E, we get vertical asymptotes. Right? These three are vertical asymptotes. And that's how we can use limit to identify a horizontal asymptote and vertical asymptotes. All right, and let's do a quick review of limit properties from chapter 2. Right? We have the sum, right? The limit of sum is the sum of limits, difference, product, quotient, and as well the number 5 is the scalar multiple, right? If you have a constant multiplied by a function, we can bring that constant to the front of the limit. And number 6, the limit of a constant is the same constant. Number 7, when you take the limit of x, the limit is just whatever the value x is approaching. And number 8, if you have the power on the function, you can bring out the power and put it on the whole limit, which results in whatever the limit value is to the nth power. And number 9, that's the nth root, limit of nth root of f. And you can do the same thing, right? Put the limit inside the radicals. So evaluate the limit first and then evaluate the nth root. Okay, so using these techniques, we are going to look at some interesting type of problems together. Okay, this is one of the properties that we'll be using a lot. Limit as x approaches positive infinity or negative infinity of 1 over x is 0, right? Because when you take 1 over a really large x value, the value is going to get very small, very close to 0, right? So when we take x to positive infinity, the limit of 1 over x is going to approach 0, right? And so we can see here and here, the lines are getting very close to the x-axis, which has the y value of 0, and we'll be using that a lot in a second. Right? And let's extend this idea to something a little different. Okay, so this is the first one. If r is positive, is a rational number, then the limit as x approaches infinity of 1 over x to the power of r is 0. Okay, so that's a kind of an extension to the previous one, 1 over x. Now we have x to some power in the denominator, and notice that here we're saying r is a positive number, so the x has to stay in the denominator, right? So whenever you get an x in the denominator, as x approaches infinity, you will get 0. And the same thing works for x approaches negative infinity. If r positive is a rational number such that x to the r is defined for all x, then the limit as x approaches negative infinity of 1 over x to the r is also 0. Okay? So basically what we're saying here, whenever you take x to positive infinity or negative infinity of 1 over x to some power, you are always going to get 0 as the limit, right? Because the denominator is just growing too fast. It's becoming a very large number. And when you punch that into the calculator, it's just too small. It's very close to 0. And that's what we mean by taking the limit as the limit goes to 0. All right, and let's see how we can apply this in some examples. Okay, before we do our example, this is the important thing that we're going to use, the algebraic way of solving this problem. First, we want to find the highest power of x in the denominator and call it p. 2, multiply the numerator and denominator by 1 over x to the power of p. Okay, so let's do this, do step 1 first. If you look at this example here, limit as x approaches infinity of 3x squared minus x plus 4 over 2x squared plus 5x minus 8. So in the denominator, we want to identify the highest power of x, which is 2, right? So p is equal to 2. Now step 2 says we want to multiply the numerator and denominator by 1 over x to the power of p, right? So in this case, x to the power of p will be x squared, right? So let's see what we have. I want to take the limit of 3x squared minus x plus 4 over 2x squared plus 5x minus 8 and multiply 1 over x2 or 1 over x squared to both the numerator and denominator. Right? And I can do that because 1 over x squared over 1 over x squared, that's a 1, right? So as long as I multiply the same thing in both the numerator and denominator, I'm fine. I'm not going to change the value of the limit. Right? And let's see what we have after we multiply. Right? So we have limit as x approaches infinity of 3x squared minus x plus 4 over 2x squared plus 5x minus 8. And I'm going to distribute the 1 over x squared into the numerator and denominator. And I'll have something like this. Okay. And after I do that, what I'm going to do is I'm going to simplify the x's if I can. And so for the first one, I have 3x squared times 1 over x squared. So the x squared will reduce each other out, leaving us just a 3. Minus x times 1 over x squared. So the x is gone, and I would still have a power of 1 of x in the denominator. 4 times 1 over x squared, that would just be 4 over x squared. And let's work on the denominator. I have x squared and x squared, that's gone. 5x times 1 over x squared. So I can, again, simplify one of the x, and then nothing here in the last part. Okay, so let's write out what we have here. The limit as x approaches infinity, I now have 3 minus 1 over x plus 4 over x squared, that's the numerator, over 2 plus 5 over x minus 8 over x squared. Okay, so now we're ready to take our limit. Right? So since we have a fraction, I can apply the limit to every term. Right? So what I will have is something like this. I can break this down into the limit as x approaches infinity of 3 minus the limit of 1 over x, right, plus the limit of 4 over x squared, all over the limit of 2 plus the limit of 5 over x minus the limit of 8 over x squared. Okay, so let's see what we have. We know that the first one, right, limit of a constant is the constant, right? So that's just equal to 3. Right? And same thing for the denominator, right? That's just equal to 2. Okay, so we have nothing to worry about there. And let's look at the rest of them. Notice that the rest of them, they all have constant over some power of x as x approaches infinity. And let's recall back from earlier. We know that when we take x approaches infinity of some constant over x, or x to some power, as long as a positive power, the limit all goes to 0. Right? They all go to 0. So what's going to happen in our example is that this is going to 0. This is also going to 0. That's also going to 0. So is that going to 0. So after we have a bunch of zeros, what we are left with is 3 in the numerator and the 2 in the denominator. And that will be our final answer. Okay. Now, of course, there are different techniques that we can use to find the limit, to find this limit specifically. Okay, so let me write it on here. So this is the summary. If f is a rational function with the degree of numerator equals degree of the denominator, okay, then when you take the limit of f as x approaches positive infinity or negative infinity, it's just equal to the quotient of the leading coefficient. Okay, so in the numerator you have the coefficient of the leading term, and the denominator you have the coefficient of the leading term in the denominator. Okay, so let's go back to the original question. The leading coefficient in the numerator is a 3. Right? And the leading coefficient of the denominator is a 2. 3 over 2, that is our limit. Right? And that's not a coincidence. Right? Let me show you another one. Let's say I want to take the limit as x approaches negative infinity of x squared plus 4 over 5x squared minus x plus 5. Okay, so first we do see that they have the same degree in the numerator and denominator. So that satisfies the first condition. And what we need to look at is just the coefficient of the leading term in both the numerator and denominator. In this case, we can see that the coefficient of x squared is 1 in the numerator, and then the coefficient of x squared is 5 in the denominator. So we can just conclude that this limit goes to 1 over 5 based on the result here. Okay. And keep in mind that the condition here is that the degree of the numerator has to equal the degree of the denominator in order for us to do this. Okay. All right, so that was the first case where the degree of numerator is equal to the degree of denominator, which is fairly easy to find, right? But that's not always the case. What if we have something like this? The limit of x squared plus 4 over x squared plus x cubed minus 1 as x approaches negative infinity. Now, in this case, we cannot use the technique that we were using before because the degree of the numerator is actually less than the degree of the denominator, which is 3. Okay, so in this case, we're going to apply the same thing, the same technique that we started with, which is using the algebraic way to solve, to evaluate this, to solve this problem. Okay, so in this case, the highest power of x in the denominator is 3. So in this case, we will call p equal to 3. All right, so we're going to do the same thing. We're going to multiply both the numerator and denominator by 1 over x to the third power. Like this. 1 over x cubed over 1 over x cubed. Right, something like that. And then same thing, we're going to distribute it. And let me write down one more step and let's see what we have. Okay, so we have limit as x approaches negative infinity of x squared plus 4 over x squared plus x cubed minus 1. And then let's fill in the 1 over x cubed right here. Right, and same thing in the denominator. Okay, so let's go ahead and see what we can simplify. So starting with in the numerator, I have x squared and x cubed in the denominator. So I can divide out x squared in both the numerator and denominator, and I will have x to the power of 1 left. Second one, we don't have any x to reduce. Now in the denominator, we also have x squared and x cubed. So I have one more x in the denominator. Second term, x cubed and x cubed will simplify each other out. So we are left with 1. And the last part, we don't have anything to reduce. All right, so let's see what we have. Right, let's write it down. Limit as x approaches negative infinity. In the numerator, I have 1 over x plus 4 over x cubed over 1 over x plus 1 minus 1 over x to the third power. Okay, so let's see. When we take limit as x approaches to infinity, we can look at each one of them one by one, just like before, right? So 1 over x, that's going to go to 0, right, as x approaches negative infinity. Same thing for this one, going to 0. That's going to go to 0 as well. The 1 here will stay as a 1, right, no matter what x value is. Okay? And the last one, 1 over x to the third power, that's also going to go to 0. So what we have left is we get 0 over 1, which is 0. Okay, so you can see that it has nothing to do with the coefficient in this case, because the denominator has a higher power. And to summarize this, this is what we can say. If f is a rational function with degree of numerator is less than the degree of the denominator, right? This is a specific case. It's not like before, right? It's strictly less than the degree of the denominator. Then we can say that the limit of f is going to go to 0. And this is very useful. Okay, this is very useful when the degree of numerator is smaller than the degree of the denominator, like in this case. The degree of the numerator is 2 and the degree of the denominator is 3, whereas the degree of the denominator has higher power than the numerator. In that case, the limit as x approaches positive or negative infinity is always going to go to 0. All right, and that leaves us with one last type of a rational function. What about when the numerator has higher degree than the denominator? Okay, like this. The degree of the numerator is 3 and the degree of the denominator is 2. So again, if you want to try this one out on your own using the algebraic way, right, feel free to pause the video now and then you can try it out. Okay, so let's see. Same thing. We're going to let the degree of the denominator to be the value p, and then we're going to multiply 1 over x to the power of p to both the numerator and denominator and see what happens. Okay, so let's see. Limit as x approaches infinity of x cubed minus 2x plus 3 over 5 minus 2x squared multiplied by the degree of the denominator, which is 1 over x squared, 1 over x squared, like that. And then do distribution. Okay, so after I do distribution and after simplifying, right, I'll have x cubed times x cubed over x squared, that's x, minus 2 over x plus 3 over x squared, all over 5 over x squared minus 2. Okay, and that's after distributing and simplifying. All right, and let's see what the limit goes to. So we have x, limit as x approaches infinity of x, that one will go to infinity, right? 2 over x, we have x in the denominator, that goes to 0. 3 over x squared, that also goes to 0. 5 over x squared, that goes to 0. And the negative 2 would still stay as a negative 2, right? Because that's a constant. So what we have here is infinity over negative 2, right? Which would be negative infinity, right? Be very careful. In the numerator, that was a positive infinity over a negative number, which results in a negative infinity. Okay. All right. And the reason is because now we have the degree of the numerator is greater than the degree of the denominator, meaning the numerator is going to grow faster than the denominator, which means the function is going to go up to infinity or down to negative infinity, right? So let's put a summary on this type. All right, so the last type, when you have degree of numerator is greater than the degree of the denominator, we actually have three cases. Two cases, right? Either it's positive infinity or negative infinity. And it's based on the three things. A, the leading coefficient. B, the leftover power of x in the numerator being even or odd. C, whether the limit goes to infinity or negative infinity. Okay? So if the leading coefficient is positive in the numerator, and in the denominator, then it's going to be positive, right? So in this case, we can see that the leading coefficient of the numerator is positive 1, right? And the denominator is negative. So positive over negative, that will give us a negative infinity, right? And in this case, x is approaching positive infinity. So a positive number to the third power is still a positive number, and a positive number to the second power is also a positive number. And that was part C actually, and part B, the leftover power of x in the numerator being odd or even. Yeah, so that was what I was talking about when the degree of the numerator being even or odd. And of course, we need to consider whether the limit is going to positive or negative infinity. Okay. And of course, this might be a little more confusing to understand. So one way to really do this without making a careless mistake is using the algebraic way to solve the problem, right? Identify the degree of the denominator and multiply by 1 over x to that power. 1 over x to that power, and then simplify and take the limit and see whether you get a positive infinity or a negative infinity. And this is for when a degree of numerator is greater than the degree of the denominator. All right, so let's look at some other example that covers everything. Now let's take a look at an example with a radical in the numerator. So we're going to follow the same technique that we were doing in the form of the algebraic way, which is right here. Okay, so identify the power of the denominator, which is right here, right? P is equal to 3. Okay, so what we can do is just multiply 1 over x to the third power to both the numerator and denominator. Okay, and the denominator is easy to distribute. Right, let's take care of the denominator first. X to negative infinity. I have 1 plus 1 over x to the third power in the denominator. And the numerator, I'm going to write this as the square root of 9x to the 6 minus x over x to the third power. Okay, now in order to include the x to the third power into the square root, this is what we are going to do. Right? We're going to use the idea that x to the third power is equal to the square root of x to the 6. Okay? In that case, if we write x to the third power as square root of x to the 6, then I can combine all the numerator together under one big square root. But here is another thing that we have to consider. Since x is approaching negative infinity, that means x to the third power is negative. Okay, be very careful. Now think about this statement. If x is going to negative infinity, a negative number, and you take that negative number to the third power, it would still be negative. That means square root of x to the power of 6 must be negative. Okay, so in order to do that, we're just going to say that we have to write x to the third power is equal to negative square root of x to the 6, right? We have to add this negative sign in front of the square root because we know that just the square root itself is actually a positive number. In order to make it a negative number, because x is going to negative infinity and x cubed is negative, we have to add that extra negative sign in front of x to the in front of the square root of x to the power of 6. Right, so let me show you what we are going to see here. All right, and let's see what we have in the original limit. Right, so we have x approaches negative infinity. Denominator is still 1 plus 1 over x to the third power. Now in the numerator, I have square root of 9x to the 6 minus x over, now x cubed, I'm going to write it as negative square root of x to the 6. And we talked about earlier why this has to be negative square root of x to the 6 versus just square root of x to the 6, right? Because of this information right here. Okay, so that's something we have to be very careful of. All right, and let's proceed to see what we can simplify. All right, so copy down the denominator first. In the numerator, I have the negative of a big square root, 9x to the 6 minus x over x to the 6 power. Okay, so I can break down the fraction in the radical into something like this, right? Limit of 1 over x cubed. And the numerator, I have negative the square root of 9x, square root of 9 minus 1 over x to the 5th, right? I can do a little, let's do a little side work here. Right, so 9x to the power of 6 minus x over x to the 6th is 9x to the 6th over x to the 6 minus x over x to the 6. Right? We can simplify the x's, leaving us just a 9 minus, and simplify one of the x. So I have x to the 5th in the denominator. So I have 1 over x to the 5th. Okay? So going from here to here, that's 1 star. All right, and from this point on out, we can apply the limit. Right? Let's take the limit as x approaches negative infinity. Right? So the 9 is going to stay the constant. 1 over x to the 5th, that thing will go to 0. In the denominator, we have the 1, which is a constant. Same thing is going to stay as 1. But the 1 over x to the 3rd power, that's going to go to 0. All right, and what do we have left? We have negative radical 9 over 1, which gives us negative 3. And that is our final answer. Now, in example like this, there is really no shortcut for us to see what's going to happen. Right? The only way we can do that is by applying the algebraic way of solving. But you can actually think a little bit about this to find any shortcuts. Right? And actually, I'll show you some shortcuts in the future. Right? But for now, I want you guys to try to work out the limit problem in this format, right? Using the algebraic way to solve the problem. Okay. All right, let's look at one more. Okay, let's take a look at this one. Very interesting. We have the square root of 9x squared plus x, and then minus 3x. But if you just evaluate x as infinity, you actually get infinity minus infinity. Now, infinity minus infinity is actually not 0. It's actually undefined, right? Because keep in mind that infinities are not numbers. They are just an expression saying that we have a really large number. Right? But exactly, we don't know what that is. So for these type of questions, we have a technique to do this, which is we want to multiply the whole thing by a conjugate. Right? So let's do a quick review on conjugates. So conjugate, let's say A plus B, the conjugate is A minus B, right? And same thing if I have x plus 5, and the conjugate will be x minus 5, right? It's just that you change the sign in the middle. So here in the original question, we're going to look at this part. That's our A and that's our B, right? So we have A minus B. We want to multiply by the conjugate. So let's do that. Limit as x approaches infinity. I have square root of 9x squared plus x minus 3x. I'm going to write this whole thing over 1, and you will see in a second. Okay, so I'm going to multiply by the conjugate, which is square root of 9x squared plus x plus 3x. Right? Opposite signs, right? That's conjugate. But I cannot just multiply it in the numerator. If I multiply in the numerator, I have to do the same thing in the denominator. So not multiply by square root of 9x squared plus x plus 3x. Oops. Plus 3x. Okay, I have to multiply the same thing in the denominator in order to preserve the volume. All right, and let's see what happens when we multiply. And another commonly used formula here is if we have conjugates multiplying to each other, a plus b times a minus b, that's equal to a squared minus b squared, right? So that's what we're going to have in the numerator, right? Because we're actually multiplying conjugates together. Right? So I have a squared, which is 9x, square root of 9x squared plus x squared. That will be 9x squared plus x, right? Minus b squared. B is 3x, so 3x squared. Over, and denominator, we just have 1 multiplied by the square root of 9x squared plus x plus 3x. All right, so let's clean up the numerator a little bit. Right? We have 9x squared plus x minus 3x quantity squared. That's 9x squared over the square root of 9x squared plus x plus 3x. So you can see that the 9x squared are going to subtract each other out, right? Leaving us just the x in the numerator. All right, let's write it down. It's going to be the limit as x approaches infinity with x in the numerator, and the denominator we have this whole thing. Okay. Now we can try to use the idea of the power, right? So we want to find the degree of the denominator. Now it's actually pretty hard to find the degree of the denominator because we do have a radical here, right? So, and then the degree of 3x is to the first power. So what we are going to do is we're going to try to look at 9x squared plus x. Now, this actually behaves the same way as x, because if you look into the leading term inside the square root, we get this thing right here, right? So if you just consider the square root of 9x squared and simplify that, that gives you 3x, which has the degree of 1. Okay, so that's we can say that the square root of 9x squared plus x behaves like 3x, right? Which has a degree 1. So we can consider that the denominator has degree 1 and multiply the numerator and denominator by 1 over x, right? Which is the algebraic way of solving. And we'll take care of all the algebra later. Okay. So in the numerator, I have x times 1 over x, which is just a 1. And the denominator, if I distribute the 1 over x, I get the square root of 9x squared plus x over x plus 3. Okay? So the 3x times 1 over x will give you a 3. And we also need to take care of this part right here, okay? Just like in the previous example. Right? Let's work it out on the side. Let's call that double story. Right? We have square root of 9x squared plus x over x. In this case, we're going to use the same idea that x can be written as the square root of x squared. So let's check again. X is going to positive infinity, right? So x goes to positive infinity. That means it's still going to be positive, right? Will stay positive. That means we can use the positive square root of x squared to replace the x in the denominator, right? So we can have square root of 9x squared plus x over the square root of x squared. Now in this case, we don't have to add the negative sign like in the previous example. All right, so let's clean this up a little bit. All right, that'll give us the whole square root of 9x squared plus x over x squared, which gives us the square root of 9 plus 1 over x. All right, and that goes into the purple box. All right, so we can proceed on with the limit. Limit as x approaches infinity of 1 over the square root of 9 plus 1 over x plus 3. All right, let's take the limit, evaluate the limit as x approaches infinity. Now, we only need to find the one where we have x, which is right here, right? 1 over x, and we know as x approaches to infinity, 1 over x actually goes to, and maybe you guessed it, 0, okay? And let's see what we have left. Right, we have 1 over the square root of 9 plus 3, which is 1 over 3 plus 3. That gives us 1 over 6 And that's our final answer. Okay. So a lot of the limit problems can be done by applying the algebraic way of solving, right? By identifying the degree of the denominator, but in some cases we do see a square root in the denominator, and we can do that by taking the square root out on its own and see what it behaves like, right? Identify the highest power of x inside the square root and isolate it and see what it behaves like, right? In this case, we have the 9x squared, which behaves like 3x, and that has a degree 1. All right, and that's it for today. In our meetings, we'll do a lot more examples with this, much more challenging ones. And thank you guys very much, and I'll see you next time.